Hello, Minjack, could you see my screen?
Yes, we can see your screen.
Oh, cool. Let me start the slide. Um, today's talk is magnetization mechanism inspired neural network. Our team come from the University of Sydney, and my name is Chiu Jie, and I'm today's presenter. I first give you some outline of this talk. I'll show you some my motivation and give you a brief introduction of material background, and then present you our proposed model. Once we have model, we want everyone can use this model. So we use 1 month to develop a graphical user interface. I'll show you the demo in later section. And finally, I'll do a summary and tell you what we are going to do next. Before we conceptualize our model, we do a literature review of the existing core loss model. We found existing core loss model can be categorized into 3 types. The first type is empirical or an analytical method. They contain stimulus equation or improved version. They are very ideal for engineering application. However, they have limited accuracy under high frequency or complex operating condition. They also are not generalized to arbitrary waveform. For the second type is physical-driven model. I give 2 typical examples. One is JA and another is precise model. They lack of speed, and the model-related parameters are hard to determine, and these parameters are very sensitive to the working condition and the material. The third type is the data-driven model. That model are emerging in recent years, and they tend to have a big model size and require lots of data to train the model, and generally are not extendable. So here comes the question. How we get an accurate, fast, generic, and data-like model? Because any type of existing model have deficiency in 1 dimension or 2 dimensions. So our team are thinking, why not we combine the advantage of different model? So we are aiming for a half physical-driven and a half data-driven model. You can also call it a hybrid model. Because our ideas start from the physics and then go to develop our architecture. I need to give you some overview of the physics behind the material, especially the core loss mechanism. So core loss is comprised of 2 components. The first component is hysteresis loss. So what hysteresis loss mean? So let's look at this microscopic image of the ferrite, and there are many magnetic domain like this circled area. So in 1 magnetic domain, the magnetization inside the domain will only along 1 direction. Then the average, the overall magnetization will be sum of all magnetic domain magnetization. Will you add any excitation to the material, the magnetic domain will expand or shrink. But no material is perfect. There are many impurity inside the material, which will block the magnetic domain movement and cause power loss. So hysteresis loss is defined as the loss due to magnetic domain movement. And the second type is dynamic component. So if you have any oscillating excitation into the material, the magnetic induction will electromagnetic induction will occur, and there will be 1 main pass, and the eddy current will be induced and follow 1 main pass. Also, along the boundary, especially the domain wall, there also are eddy current induced, which are called local eddy current. We tend to combine this both current together into one component called dynamic component. So I understand this may hard to understand for people who don't have material background. You can analog to fluid dynamic. So there are friction and viscosity in fluid dynamic. So hysteresis loss is similar to friction loss, and the eddy current loss is similar to the viscosity loss. So here we come the final power loss equation, and eventually you can derive the total magnetic field strength as the sum of two components. Next, we are going to tell you how to model these two components. For the first component, hysteresis, in classical model, a classical physical-driven model, people tend to use operator, like hysteresis operator to model this effect. Hysteresis operator theory assumes there are many infinite operator inside a material. And the average magnetization will be the sum of all operators. And the operator volume represents the magnetization inside a tiny area. Even there are infinite operator, we can still categorize them into some category, into finite category. But now the challenging thing is to how to define the proportion of each category, of each type of the operator. This is the most challenging part for the traditional hysteresis model. But now we have powerful tool, we have AI, we can use AI to help us to determine this coefficient, and we'll do this in our model. For the next part is a dynamic component. You can trace back to the stimulus equation, also the loss separation law. You'll obtain this analytic equation. It's quite simple. But this equation can only applicable under low frequency, because in high frequency, you will have skin effect, which makes your flux density and eddy current not uniform across the whole cross-section. So to alleviate this effect, we use segmentation. We assume there are many segments in the cross-section, and inside each segment, the flux density and the eddy current is uniform, so that we can use this equation. Similarly, the most difficult part is to how to obtain the coefficient, the global eddy current coefficient and local eddy current coefficient. We also will use AI to help us to do this part. Finally, here come our proposed model, magnetization-inspired neural network. We follow the main equation. So we have two subnetwork, and in the upper subnetwork, we use to predict hysteresis component. You just need to input the dB, and you can get the operator value. We use one layer AI to predict the operator density function, and you weighted sum all operator to get the hysteresis component. And for the lower part, we use to predict dynamic component. We follow this equation, and we can simplify this equation into another form. From this equation, you can easily find the input is BFT, dB, and dt. So we use them as a input of the neural network. And we use one hidden layer to predict this nonlinear function, and another layer hidden to output layer, the weight to predict the coefficient. You can regard this nonlinear equation result as a magnetic field strength along one segmentation. Eventually, you sum the two components together, and you will obtain the final magnetic field strength. Our model is point-to-point model, which means you can only input one flux density and return a magnetic field strength at a certain time. If you input a cycle of excitation, you will obtain a BH loop, and you can also get the color density. The most exciting part is our UI, and we use the last month I used 1 month to develop this UI, and it's based on the sorry, I need to stop there. I based on the QML language, and I'll show you directly on my laptop. I already packaged everything into an executable app. You can open it. Then here is the home main page, and this page help you to calculate the colors of one cycle of excitation, and you can change different type of waveform, and you can play around the amplitude, phase angle, initial phase angle, also the duty cycle. We also allow user to customize your input. Once you well define your excitation, you can select which material you are aiming for. For example, we select N27. And here we'll show you the model confidence of the current trend model, and you can click predict. And it show you the BH loop and also the waveform of the field strength and the core loss density. If you want to see more detail, you can hover over your mouse and to say each point value. By the way, you can play around with frequency and temperature to see different results. We also have another page which allow user to input not only one cycle. Instead, we can input many cycle. You can input a testing data set. You just select your material and input your CSV file. All file follows the format of the MagNet challenge and BFT, and then you can download the core loss density into a CSV file. If you already know the actual field strength, you can also upload it and click predict. This will then it will return a histogram to show the prediction, the error, the relative error between the prediction and the estimation. And this four stuff will show you the statistics, like this graph. Okay, let's back to the final PPT, and here is a summary. So today, in this talk, I present you a hybrid model, which is based on physics and some core loss mechanism. So it's explainable and accurate and fast than other fully data-driven or fully physics-driven model. We can also make this model only use a small amount of data to train it. And every training come from the scratch. In the future, we are going to add these bias, and we are aiming to deal with arbitrary waveform until we can solve transient state core loss estimation. For example, we wanted to deal with a BH loop contained a minor loop. Yeah, and I think that's all. That's all of my talk, and thanks for your listening, and feel free to ask any question.
Very good. Thank you, Zhujie. Very nice presentation. And I can tell you that University of Sydney is really a competitor in the performance track, in the novelty track, and in the software engineering track. Congratulations on demonstrating such a great initiative, like with all the innovations from fundamental to software engineering.
Yeah, thank you.
Yeah. So I think it's very exciting. Are you planning to open source your tool, or you're going to think about commercial? Like you mentioned, that you guys have interest in developing this into a commercial product.
I think this depends on my supervisor. I've discussed with him. His suggestion is after we publish our paper, we can open source our code. But this tool we will keep it because we want to further develop other other algorithm, and because we can add another page, and this is kind of my my thesis work. So
Yep, yep.
I'll keep the tool, but I may open source the code, I guess.
Yeah, this is super exciting. No, and there's there's no pressure from our side. It's all your decision. I'm just very curious and very excited to see all these developments coming.
Cool.
Yeah, I hope that we can have a tool. Every one of us can have a tool. And also, right now you are probably using the data from us. You have 15 material. If more teams join us, if we do this as a community, then if there's a new material, suddenly we can probably have like 100 materials covered. That would be super nice.
Yeah, that's true.
Yeah, right. Now for the minor loop, is
Mm-hmm.
I just want to make sure.
Yep.
You are using a neural network approach, and you are taking a time domain B as an input information. You should have already covered minor loop situation, right?
No, we've already tested it, but it doesn't work. I guess we lose some mechanism when we try to model the hysteresis part, because hysteresis also should have memory, like the BH loop. You can see there is a turning point. So in the static hysteresis, we also should consider the memory. But in our model, we don't have memory. I think the problem comes from here. So we should add this mechanism.
So if you just learn from all the some other teams have used models with memory, replace it with this, or add some memory effects into your network, you should be able to capture that, right?
Yeah, I think so.
But for the transient, that was what I was thinking. It could be one of the future challenge. Right now, we don't even have a data set for the transient. Yeah, and it's tricky. And we don't.
Yeah. But from our review perspective, we think if you capture all mechanism, you can you don't have to train with any transient data. You can only train with the steady state periodics data, and it should work. It should work with transient.
But the question is that you don't, without seeing the real world data, you can't say your thing's working.
Yeah,
right?
That's true.
It's a chicken and egg problem. You need to have one set of high quality data.
Yeah, that's true.
Yeah,
I agree.
Yeah. Anyway, any other question from the audience and the organizing team?
I think this is a very good solution. Like you combine the physics mechanism and with the neural network, doing a hybrid neural network. I suppose it have better generalization capability compared to the pure neural network, which is more tend to do overfitting. So how do you feel like your generalization capability to different waveform types? For example, I saw you did pretty good in the waveform in the material D, where we provide only a little bit of the trapezoidal data. And what do you think about just like, for example, the one you said about the minor loop and the transient waveforms?
I guess the main reason we did bad is we didn't put all mechanism into our model. So because I've already tried with a new version of my model, and we add some memory part like LSTM into the hysteresis subnetwork. The average error and even 95 error will get much improved. So I guess that's the reason why we did bad in some material.
Okay, great. Any other comments? No? Okay, then let's move on to the third team, Southeast University Xu Wei team from China.
Okay. Can you looking?
Yes.
Okay. I'm going to be invited to